And thanks all of you for coming. It's really great to be here and to share the work that my group is doing with all of you. So the topic that our lab is very interested in is computational design for compliant dynamical robots. And to get us into this topic, I thought I would start with, the idea behind computational design, right? So the idea behind our group is we're trying to make robot design more accessible to the general public. We're trying to think about how we can get anybody to be able to design a custom robot that they want. So let's say this is you, and you have an idea for a robot that you want to create. Maybe you have some idea of some general morphology, or you know what task you want it to do. Well, in the future, we imagine that there will be systems that will be able to help you to create that design, right? Even if you're not an engineer, it'll be able to ask you for specifications, help you make design decisions, and then very quickly take that idea and turn it into a real physical robot that you can bring home with you and use for your particular task, right? So when we're thinking about this sort of problem, how do we set it up? Well, first of all, we have to be able to describe what is a robot, right? And so the way we think about a robot is, well, it has links and joints. This is a description that you all are probably very familiar with, right? Because this is a description people use in URDF files for robot descriptions. So the links include geometry, inertia, other properties corresponding to the robot's physical parts that take up volume, right? And then the joints describe degrees of freedom, ranges of motion, control, etc., right? And so the robot, when we're thinking about it, is a graph that contains these parts, right? In addition, if we're trying to make custom robots for different types of tasks, we need to think about what is a task, right? And so in this case here, your task is a combination of an environment, which you want your robot to be living in, and some sort of objective for what you want your robot to do, right? And so if we have this sort of specification, then robot design, you can write down using this very simple problem formulation, right? So we want to maximize our objective, F, over the space of possible robots subject to physics, right? And so this is how we have tried to more formally think about the problem of robot design. Of course, I've hidden a lot of details in this description, right? But for different types of robot descriptions or different types of task descriptions, you can get different types of designs or different types of algorithms that allow you to solve this problem. So when I was doing my PhD at MIT, we thought about, well, what if we want a robot that's going to walk forward in a flat ground, and the robot is just a kinematic chain, right, made of rigid bodies and rotational joints, right? So in that case, what we can do is we can build these systems that allow you to compose different types of robot geometries with different types of kinematics, and to simulate how they are able to locomote forward on a flat plane. And if all of the geometries are resolved inside of the software makes sure that the controller makes sense, that the robot can be fabricated, then we can take this design and we can convert it into a fabrication plan, which then you can follow and have a robot walking around in front of you in about 30 minutes, right? So these are the sorts of designs that we know we can create with a little bit of help from a human, in this case, who is interacting with our software. We're, of course, not the only people who have done this. There's a lot of approaches that people take towards this problem. So what you're seeing on the bottom left here is another system that was developed by Stelian Koros's group back when he was at CMU. And they were interested in, well, how do we also incorporate the electromechanical components, the sensors, the motors, and make sure that they have a place in the robot body. What you're seeing in the middle is additional work where Encore Meadow was thinking about, well, how do we also take into account the rigidity of the parts that need to be created and how the fabrication strategy affects how rigid those parts are. And so different systems over time have been trying to solve this problem of computational robot design and have come up with different solutions for different aspects of the problem. So we've gotten a lot of functionality out of these different systems. But one thing that I'd want to note is that if we go back in time a little more, unfortunately, the way that we solve these problems and the ways that we think about these problems compared to approaches that showed up around 20 years ago are not really fundamentally different. In that back in 2000, there was also this idea of, well, let's describe a robot as a graph made of rigid components and joints, and the joints have a controller, and the task is to move forward on flat ground, and we can evolve this robot, and we can also fabricate it, right? And so these approaches that we've been using in order to make more interesting robotic structures, they allow us to think about different types of tasks, but fundamentally the representations that we're using for the robot and for the task have not changed. At the same time, when I show these videos to people, they always look to me and they say, well, those robots look like toys. They're not actually going to do anything, right? And so these assumptions that we've made in order to build these sorts of systems give us designs that move. They can move forward on flat planes, right? Sometimes they can move forward on more complicated environments. But the resulting physical designs that you see often are not really going to work on a real task that any of you might be using your robots on, right? And so when I started at Penn, I started thinking about this problem, and I said, well, we really want to make sure that the robots that we're creating these systems for are actually useful. And so let's compare the robot that came out of my system to something else that somebody else built, right? And so here, I took a video from Steve Cullen's group. You can see here an example of this system, which is allowing someone to actually walk over irregular ground, right? And so this is a system that some engineer has actually built, right? And if you really wanted to look at the very high level, the task that it is trying to solve is the same as the one on the left, right? But there's a fundamental difference in the way that these systems are designed. And so one of the observations we made was really in the compliance of the system, right? And the fact that the task on the right is dynamic, right, is dynamical, and the task on the left is really not. And so recently, my group has started to think about this problem, where the major insight is, well, if we want our robots to be actually useful, then the ability to manipulate energy is key. And of course, this is not a particularly new insight, right? People have known for years that there's this slip model for walking. And so if you want to be able to model how biological systems walk or how energy efficient robots might walk, then you can model it as some sort of spring-loaded inverted pendulum system. And the way that we design these systems is really about energy transfer, right? How we think about how potential energy and kinetic energy change or exchange. And so this is really the inspiration behind a lot of the work that my group has started to do recently, where we're still very interested in this idea of computational robot design, and we want to think about how do we make robots for custom tasks, but we've started to integrate ideas of compliance and energy efficiency. So we've done a lot of work now in compliant mechanisms, how we can create different structures with programmable compliance properties. We've also thought about reconfigurable structures in the sense of, well, if I have a robot that I've then tuned for a particular task, are there ways that I can manipulate that same design in order to get it to also perform other tasks? And a lot of the work that we've done is also origami inspired, in that these designs that we've created can be fabricated using folding, which we think there's a lot of value in because it allows us to directly embed electronics and actuators directly into a sheet that then we turn into a 3D robotic object. But combining all of these ideas together then, the main problem that we've been thinking about is, can we computationally think about how we can then use compliance in order to enhance the capabilities of a robot design? So I'm not going to have time to talk about all of these projects today. I was going to focus in on a couple, but I'm happy to talk about other things as well if you all have questions about them. So thinking about the problem of computational robot design and compliance, then one of the first places that we went to was topology optimization. Some of you may know that topology optimization is has been pretty successful in designing structures when we want to think about, well, what is the mechanical response of that structure? So if we want to build a bridge, for example, or if we want to basically think about how a 3D object is going to respond to forces applied to different areas, we can start with a block of material, and we can model the physics of that block, and we can change the density of certain areas of that block in order to manipulate the response, right? And so topology optimization is an approach that people have used to try to solve the problem of, given a block of material, what is the particular distribution of densities that I want in order to produce a particular response. And what you're seeing here is an example of that type of formulation. So here, what we have is some type of objective, right? Some type of force or energy that we're trying to achieve. We have the material density on the left. This is the object that we're going to be building. And we have some physical model for how the material deformations change as a function of the input forces, right? And so in addition, you sometimes have some fabrication constraints, right? And so these sorts of approaches, like I said, give you interesting complex structures that produce some sort of mechanical response to given inputs, right? So in this case, what these authors were producing was this bridge where there's a point load in the middle, and they were trying to minimize the compliance of that bridge. What you're seeing on the right is if there were radial forces, then by solving this optimization problem, you get a wheel, right? And so these approaches have often been applied to static scenarios. So we wanted to know, well, if now we want to take these ideas and then do computational design for a robot, can we take some of the same approach, right? And the form of this problem you're seeing is very similar to the form that I showed you on the first slide, right? So one of the areas where we wanted to apply this was, we were saying, well, what is an interesting, complex, and dynamical task that we might want a robot to achieve? And my student was very inspired by the idea of hybrid aerial vehicles. These are vehicles that have two different modes of flight, right? You have this multi-copter-based mode, which is supposed to be highly agile. You can have vertical takeoff and landing, and also a fixed-wing flight mode, which is highly energy efficient for long-distance flight. And at the same time, we saw this video out of Mueller's group, which is this reconfigurable quadrotor that can morph in order to get through small spaces. And we said, well, what if I want to take this idea of passive reconfiguration and use it to design some sort of hybrid aerial vehicle that can switch modes? And what if, because this is a very complex task, what if maybe we try to solve it using topology optimization? And so the idea behind this project was this. Jessica Weekly is the student who was leading this project, and it was a collaboration with Chen-Fan Fu Jiang's group, he's at UCLA, and specializes in simulations for deformable bodies. So the idea here was that we would take this quadrotor, right, and we would put in compliant structures, and we would attach a wing deployment mechanism to this compliant structure so that when the vehicle accelerated, then this compliant mechanism would switch, and then the wings would fold in or out, and we would be able to get this vehicle that switched modes passively by using just the actuators that are on the robot itself. So in this case, what you're seeing is a video for when imaginary rotors that are at where those orange arrows are pointing apply bursts of thrust, and the mass in the middle right here accelerates or decelerates in order to switch the mechanism back and forth. So this problem here, we thought, well, this mechanism in the middle, ideal application of topology optimization, but we're going to be applying it to this really interesting dynamical task. And so we formulated the problem. It looks a little bit more complicated, but the form is exactly the same as what I showed you before. We have reaction forces that we're trying to optimize. We have some fabrication constraints. We have actuation constraints. And using that, we started with this material block, which then we basically optimized using gradient descent and Chenfang Fujiang's deformable body simulation. And we ended up with a beam that looked like this, which produces, a mechanical response that looks like this. And so the idea here is that through this optimization, now we were able to achieve this bistable mechanism where each of these beams is attached to the frame of the quadrotor, and we have a big mass in the middle, right? So changing the location of this mass results in reaction forces from these beams that look like this curve. And so if the vehicle accelerates and this platform is pushed past a certain point, right, this 0 right here, then the vehicle will automatically switch modes, right? And we said, this is really great. We didn't actually have to do any of the manual design ourselves. Can we get this robot to actually work in real life now? And so we printed out these beams and we attached it to a quadrotor, had it accelerate. And what you're seeing now is a comparison of the physical vehicle with the simulated one on the left. So this vehicle over here is going to accelerate, and now it's decelerating. The mass in the middle continues its motion because it's, the actuators aren't directly attached to it. And as a result, the vehicle switches modes, right? So we were really excited by this result because we think it's the first time that topology optimization has actually been applied to a dynamical task as opposed to just a static one like the ones I was showing you at the beginning. And so Jessica took this vehicle and she attached wings to it. The wings are fake. They're just there for visualization. But we put the quadrotor in the air and we said, well, will it actually be able to switch in the air? So here's the video. The vehicle turns, right? And then it accelerates and decelerates. And what you're seeing now is that because this mechanism switches in the middle, then the wings deploy. I'll play that for you again. And if we track this vehicle in the motion capture system, then what you're seeing here in the yellow dots are the relative location of the center platform compared to the frame of the quadrotor. And you can see that there's a very clear transition between when the platform is down relative to the frame, that is, the wings are folded in, and when the platform is up. So we were really excited about this because we said, well, okay, we used topology optimization to automatically design these compliant arms, which allowed us to get basically passive switching between modes for this hybrid aerial vehicle. And we didn't have to add any additional actuators other than those that were already on the vehicle, right? All of this transition was achieved just through acceleration of, just through the control. Yes?
I have one question about how you framed the optimization problem, or more like how you solved it. Did you have to make some tricks about making it differentiable? You said you used gradient-based optimization. Was it
Yes.
Do it, or did you have to make some approximations?
Okay, can you repeat the question for the people?
Yes. The question was about how we formulated the optimization problem, and specifically about how I said we use gradient descent, which requires gradients. And this is one of the reasons why we were using Fanfu's simulation. It's a multi-point material method simulation, which is differentiable. So so all of the gradients were calculated. Any other questions? Okay. Great. So, like I said, we were really excited by this result, but you'll also notice that I paused the video at a very convenient location. So if I continue to play the video, what you'll see is that the vehicle flips over, right? part of this is because the wings are, like I said, fake. They're just there for visualization so you can see them deploy. But another reason for this is because of the dynamics of the vehicle. So if I play back this video again, it should be clearer what's going on. And actually, this video over here is probably clearer. The assumption that we were making when we designed the controller was that the vehicle was symmetric, right? But it's very clearly not, and that there's tilting in the platform because of gravity, right? And so as a result, when the vehicle switches states, then there's a huge counter torque that gets induced that causes the vehicle to go out of control, right? And so this was, basically what happened was that when we formulated the problem, we weren't thinking about this, right? We made assumptions about the symmetry, and we neglected to take into account some other effects of the vehicle, right? And so we're currently trying to figure out, well, can we incorporate those sorts of design criteria into our optimization problem? But at the same time, it started getting really complicated. And we said, well, are there other approaches that we can take to try to approach these sorts of dynamical systems from a computational approach? So those of you who are interested in computational design have probably seen this pair of papers that came out in the 1990s, where people have been thinking about these sorts of problems. And there's a really interesting comment from Daniel Whitney where he said, mechanical design cannot be like VLSI design because of interdependency between the parts, kind of like what you just saw with the HAV. VLSI design and programming compilers are very modular, right? In that if you design a particular subcomponent and you put it into the rest of your design, it will work the same way every time, right? And the behavior of that component doesn't depend on whatever else it's connected to. But that isn't really the same when it comes to mechanical structures, right? So if I attach my compliant beam to this frame on the quadrotor, and there's something else in the system that's causing a different mass distribution, the vehicle's behavior is going to be different, right? And so his claim in this paper is that, well, compilers for mechanical designs just aren't going to work. Right after that, there was another paper, there was a response from Eric Antonsen, who said, well, that's kind of true, but instead of just saying this problem is impossible, maybe what we should be thinking about is, well, when can we take a modular approach, right? There are some cases where you can design parts of your system and approximate all of the other stuff so that you don't have to take all of the interdependencies into account. And what we should be thinking about, instead of just throwing up our hands and saying it's not going to work, is, well, when is it possible to take that approach? So this is kind of the other approach that we've been taking in my research lab is, well, we're trying on one hand to really optimize the entire system, and we're continuing to work on the HAV now. But on the other hand, we're also trying to think about, well, can we modularize the design, and can we think about individual compliant mechanisms that then we can combine to create these more interesting dynamical behaviors? And when is that possible to do without trying to optimize the whole thing? So before I continue, are there any questions? Okay. So the idea then, the other approach that we've been thinking about in the lab is this idea of design composition, right? Where I have a library of parts that maybe my lab has designed, or maybe you've designed, or somebody else has designed, and we know that it works for a particular purpose, and we can drop it into a library. And this library of parts has some high-level representation of what each of the parts does, right? And now if I want to create a new design, then I can identify each of the parts in my new design with something that's in the database, and I can combine them together. And because each of the parts in the database is also fabricatable, then the new design can also be fabricated, right? And so this sort of modular idea is the idea that is taken in programming and in VLSI, and it's the sort of idea that we are hoping you can take in certain mechanical design scenarios. And so one of the places then that we've been starting to focus is, well, we have these modules that we want to combine together. Some of your robot components are going to be rigid bodies, which we know how to create, but some of them are going to be compliant bodies because, as I said before, we need to have compliance in order to manipulate the energy of the robot, right? And so we've been trying to design robot parts with programmable compliance. And one of our inspirations here has been the Bellows theorem. The Bellows theorem is this result in computational geometry, which says that if you have a structure and you want to change its volume, you cannot do that if the faces remain rigid, right? So the picture you can have in your mind is of like a cardboard box, right? So if you have all of the faces on your cardboard box and they're fixed, that cardboard box is rigid, right? It's not going to collapse unless somehow you deform the walls of that box, right? So what that means is that if we have a structure and we want to change its volume, inherently, those faces need to deform, right? And that deformation means that the structure is storing strain energy, right? Which means that it has some sort of compliance or some sort of stiffness associated with it. And further, that the stiffness of the structure is related to, how much of the face is deformed, which we can compute geometrically, right? So what you're seeing here is an example of a bellows structure that we've been investigating. It looks like this, right? It's a bellow. It has this accordion fold pattern, which is typical of bellows structures. And up on the right, you're seeing my student compressing the structure. It's made out of thin poster board, but it is quite stiff. And the reason it can be this stiff is because the faces need to deform in order for that compression to happen, right? Not only that, but the geometry and the amount that the faces deform are going to depend on the particular geometrical parameters of this structure. And so if we change, for example, this alpha angle, which is in the fold pattern that's corresponding to this 3D shape, by even just 1 degree, we get a huge change in the mechanical response. And so what is really nice now is that we can design the behavior of these structures purely by changing their geometry, right? So based on these ideas now, we can basically come up with modules that are also parameterized by geometry, but that result in different compliance, right? And so what you're seeing here are some experiments that the students did to try to figure out, well, what is the range of compliance that is achievable for this bellows structure? And what they found is that the stiffness is pretty predictable. And it's, in this case, there's a very nice linear relationship between the stiffness of the structure and the angle of the fold. So we can take these ideas then and we can use these modules in particular designs where we want to get desired compliance. And we can choose the particular parameter associated with whatever stiffness or compliance that we want, right? Now, as a side note, what I'm showing you here is a folded structure. And you might be wondering a question that I get a lot, which is, if you deform this thing over and over again, isn't it going to tear and break? So my student also got very invested in this question and put this the bellows that you see on the left through a cyclic test over thousands of cycles. And what you're seeing here is a typical curve for an origami structure, which is that the first cycle is very different from all of the others, but the structure very quickly converges to some sort of steady state cycle, which is then consistent over all of the following trials. And so even though these devices are folded, we can use them over many, many cycles, and they survive quite a long time. And the reason for this is because actually the facial deformations that are happening inside of the structure are relatively small. So the material doesn't actually have to stretch that much and it doesn't tear. So going back to the module though, what we can do now is design some sort of robot, right? Where if we have some particular desired stiffness in mind, we can now design the compliant part to match that stiffness. What you're seeing here is an example of a robot where we actually did that. this is a jumping robot where the top is 2.5 kilograms of just motors and the controller and power and all of that stuff, which is basically the payload of the robot. And using what we know about this payload, we can tune or we can figure out what is the necessary stiffness of the legs on the bottom that are being used to get this robot to jump. And we can basically design these springs to give us that stiffness. And what you're seeing here then is that design jumping forward consistently with a very simple Weber-styled controller. And the thing I want to emphasize is that, one, the design was created out of this parameterized module. And two, that the springs that are being used to carry all of this load are actually quite light. It's only 50 grams of folded material. Not only that, but because the structures are compliant, then that same design can actually locomote over a wide variety of terrain. So here you're seeing that exact same design with the same controller hopping over this obstacle course that the students set up. And of course, the speed at which it moves is going to change depending on the particular environment, but it is still able to achieve this hopping behavior. So one place where we're trying to take this project then in the future is thinking more about, well, how do we then integrate or how do we then take advantage of the fact that we're using origami-inspired fabrication here? And just as a side note, one of the places that my group is very interested in taking advantage of these structures is so that we can directly integrate all of the actuators and electronics. So we've developed these planar fabrication approaches that you can use to put your circuitry directly onto the structure. And hopefully we can get rid of that huge mass of motors and wires and everything that's on top. So when you do this process of basically taking your circuit, transferring it onto a sheet of plastic film, which is then essentially a flex PCB, we laser cut folds into the PET film, and then we fold it by hand. Then you get these circuits that look like this if you put it on a rigid plate, or that look like this if you put it on a thin sheet of material. And if you also take advantage of, if you also put a layer of smart material sheet in the middle, you can also get these structures to self-fold. So using these sorts of ideas, then we can take these circuits and then we can directly transfer them onto these jumping designs that I showed you, and then we can have these fully untethered jumping systems that look something like this. This is the exact same bellows pattern that I showed you on the previous slide, but there's only one layer now instead of all of the layers. And all of the motors now are directly embedded inside the fold pattern. All of the circuitry is directly on top instead of us having these large aluminum frames. And so these structures can jump very similarly to the larger scale robot that you saw previously. And again, just like the robot you saw previously, the geometric parameters that control the jumping energy for the structure can be changed in order to get, in this case, different jump heights. So basically, then we have these modules of compliant structures that have different parameters associated with different designs, right? And then the question we now need to think about is, well, if we want to be able to compose these designs together, can we do that? Like, can we always do that, right? Or can we always do that in order to get a particular type of response? And so one of the places where we've been focusing that question is first in manipulation, because this is arguably the easier design problem. And the question we've been thinking about instead of just thinking about, very dynamical robots that are flying or jumping, is just if we have a particular kinematic structure that we want to achieve with a particular compliance profile, can we use this sort of composition design approach in order to achieve that design, right? So the problem looks like this. We're representing our manipulators with a DH specification, and each of the joints in this DH specification has a certain stiffness associated with it. And what we want to do is try to solve this subproblem, right, of converting this kinematic chain directly into an origami pattern. Now, what's really interesting about this problem is that, here's an illustration of the problem. So what's really interesting thing about this problem is that because we're taking a modular approach, we can divide it into two parts, right? And the first part is what is required in the database, right? In addition to that bellows that I showed you on the previous, in the previous section, what other additional parts do we actually need? And two, can we guarantee that these parts can be composed, and how do we compose them in order to achieve a particular kinematic chain, right? So my student Wei Shi has put together an expanded database of parameterized parts. They give you different geometries and different degrees of freedom. And we've started tackling this problem of can we compose these structures together, right? So the main insight that we've had in this section is, yes, you can automatically convert a DH parameterization, a DH specification of a manipulator directly into an origami structure because your DH representation dictates the locations of all of your joints, but only up to a translation. And so we can take advantage of this extra degree of design freedom in order to design the particular robot we're trying to create. So our main result here is that given this set of modules that can give you rotation, translation, both as a free degree of freedom or just as a rigid transformation, and the fact that all of these modules are parameterized, so we can get a particular range of motion out of each of the joints, a particular geometry out of each of the rigid parts, we can always construct a tubular crease pattern that corresponds to a desired DH specification. And this is, and we have a provably correct algorithm that will allow you to do this. Not only that, but because the compliance can be specified, then you can also add that into your specification. And the reason we can do this is because of our main insight at the top, but also what we found was that if we drill down into the specifics of the problem definition, you can actually map this problem to a Dubin's path planning problem, where there's been a lot of work in computational geometry. So we can basically take all of the work that people have done in 3D Dubin's path planning and apply them to this manipulator design problem. So what does that look like? Well, if you're interested, you can download the code and try it yourself. But I'll also walk you through what the algorithm looks like. Basically, if I have these joints that I want to connect together, then essentially what I'm doing is I'm taking the end of one joint and trying to connect it to the beginning of another joint. And those are two joints that are on this kinematic chain, right, that's forming my manipulator. And if I want to connect these two joints together, then I can construct a Dubin's path between them, right? This path has both circular arcs and linear components, and each of those sections can be converted into a fold pattern. So what that means is that if I have a joint that I want to connect to this side and a joint I want to connect to that side, I can always connect them with an origami pattern so long as I can construct this Dubin's path. And results from computational geometry tell us that this path always exists so long as the joints are more than a certain distance apart, right? And so what I can do now is I can take my desired manipulator design and I can figure out well, where are the joint locations that allow me to get this distance apart and allow me to construct these links between them, but still maintain the desired degrees of freedom according to my DH specification. So what you're seeing here is that process where for each joint, I can move it along its axis of motion without changing the actual degree of freedom that that joint provides, right? And I can move it until it's more than the desired distance away from the previous joint, and I can do this in sequence. This allows me then to construct these Dubin's paths between the joints and to construct this origami pattern. And the resulting design here is exactly corresponding to the DH specification that was provided at the beginning, right? So once I have this pattern, I can fold it. And what you're seeing here now is the origami pattern corresponding to the desired compliant kinematic chain. Now, this is not a chain that you would probably ever want to use in a robot because it's extremely complicated and larger than it needs to be. But I think what's really nice about this is that now we have provable guarantees that any kinematic chain you want to produce is possible, right? So as an illustration, we took the Puma arm, right? This is a 6 degree of freedom manipulator. We asked the algorithm to design as a Puma arm. What you're seeing here is the path of links that corresponds to that arm, and each of these spheres, these colored spheres, is one of the joints. This, like I said, it's much larger and more complex than you would want it to be, mostly because of the additional space we needed to add in order to prevent self-collision. If we drop some of the constraints that are needed in order to avoid self-collision, we get a structure that looks like that, and these are at the same scale. And if we add a human in to actually place all of the links for us, then we get a nice complex Puma arm equivalent, which then we can fold into an arm that looks like that. So essentially, what we have shown now is that at least in the space of manipulation, we can get an arbitrary kinematic chain with a desired compliance profile out of a modular design approach. Any questions? Yep.
I have one. Maybe I missed this. Did you answer the question of what components are actually necessary, or did you fix this one now?
Yes.
Or was it like, given the components, this is what you can do?
Yes. So basically, I kind of lost it for that a bit. So basically, what we showed was that if you want to construct this sort of arm, it is sufficient the sufficient condition is that there is a Dubin's path between the joints that you are trying to connect together, right? So in a DH specification, there are two different types of joints. There's your revolute joint and your prismatic joint, so we needed modules at least for those two. And then if we wanted to connect them together with rigid links, we needed to be able to actually fabricate that Dubin's path, which corresponds to a circular arc module and then a linear translation module. So it turned out for this problem that we actually only needed 4 different types of modules, one for each of those components. Any other questions? Yep.
So is the prismatic link actually sliding? So I guess that part is not technically origami, but it's nonetheless still being constructed with the same material?
Yes. So it is actually origami. And so the prismatic joint is based on the bellows that I started with, where you can compress it, and then we added in these walls on the side to constrain the motion so that it doesn't bend. So this is still folded out of one sheet of paper. It's just kind of folding back on itself. No problem. And then here's the revolute joint. And then these 2 modules over here are our rigid components. This is for the circular arc, and that's for the translation. Any other questions? Yep.
So we saw before when you were like showing how the initial your initial like folding mechanisms, the initial like load and release is very different from when you do like up to 2000. I'm wondering, like for this case, when you're looking at how accurately you're able to like realize the DH parameters, like is that something that difference? Is that something that you have to take into account in the planning? Does that just come out in an inherent like error in your?
Yeah.
In your?
So basically, what we showed was that if you want to construct this sort of arm, it is sufficient to Yes, good question. So I showed in our cyclic test that there is actually some hysteresis, right? So back in these plots, the curve on top is when you're compressing, and then the curve on the bottom is when you're releasing, right? And so the two curves are different. For the purpose of the design algorithm I just told you about, we took the average. But yeah, in the future, if we wanted to get like very exact stiffness in both directions, right, we would have to take that into account. The other comment I want to make is that the amount of energy that you lose, right, when compressing and decompressing, or like the difference between these two curves is also very material dependent. So this was for poster board, right, that you can get from like a regular art store. If you used a different material, then you could also get those two curves closer together. Other questions? Okay. So basically, the idea then that we're thinking is that since we can take an arbitrary kinematic chain and then convert it into a physical design, or I mean, we can take an arbitrary DH specification and turn it into a physical kinematic chain design, right? Then we can incorporate this as a module inside of our overall robot design approach. So let's say that you have a robot that you want to have a certain type of mechanical behavior, then that gives you certain control requirements, but it also gives you your compliance specification, right? That robot is going to interact with the environment, right, which will give you some external forces that your robot needs to respond to, and all of that results in your final robot's interaction with the environment, right? And if you want to be really specific about it, then all of those parts also feedback and they interact with each other, right? But the particular part that we've been concerned with is this yellow box, and the way that we think that you can approach it now is if you have your motor control coming in, your mechanical feedback coming in, and these are parts of your design specification, then we can turn this into some sort of DH specification for a part of your robot. We can choose the parts corresponding to the design. We can choose the relevant mechanical properties which map to geometric parameters, and then we can compose them together using these composition approaches. And then we can put them on our robot for the particular type of motion and stiffness that we want to achieve. Okay. So I had some other stuff I want to talk about. I think it's time to wrap up though.
7 minutes until end of Q&A.
Okay. So I'll quickly move you through some of the other projects where we've been applying these ideas as well then. One question that we've been thinking about is, well, what is the particular compliance specification that you might want to use within the context of manipulation? So in this case, we've been working on more theory now on trying to figure out if you want your robot arm to stabilize around a particular end effector position, how do we actually figure out what is the distribution of stiffness throughout the arm in order to achieve that end effector position with a certain amount of stability, right? And what we've shown is that for a particular serial manipulator, if you model it as a network of springs, then we can derive the forward kinematics of that structure. We can figure out how it deforms when certain actuation is applied. And actually, if we want it to converge to a particular end effector position when a given when a particular input is applied, then we can solve for the resulting distribution of stiffnesses, again, using gradient descent. And so basically, here's an example where if I have like a 3-link manipulator arm and I want it to converge to that purple triangle when I just pull on a tendon down the middle, so there's only a single actuator input here, then the stiffnesses need to be designed according to a particular distribution, which you're seeing both pictorially on the right and in graph representation on the left. So what you're seeing here is that the thinner lines are softer, the thicker lines are stiffer. And so in order to get the robot to converge to that end effector position, we need a asymmetrical stiffness distribution, right? Not only that, but because we have a lot of different parameters that we can manipulate in order to, in this design, we can achieve a particular stiffness profile, right? So if I want the end effector to maintain that end effector position with a certain stiffness, then I can scale up or down the stiffnesses along the length of the manipulator in order to achieve that response. So that's one example where we've been thinking about how we can actually create the specification. And then in addition, we've been thinking about other application areas where we can apply these ideas. So another project that we've been working on is in the domain of underwater vehicles, where again, you can try to use a soft design in order to produce, in this case, forward locomotion. So what you're seeing here is another origami pattern that, again, is parametrized, and that and it produces a certain deformation and force response when it's compressed. Right, so what you're seeing here is this pattern in the air, where there's a motor in here that's just causing it to contract. The volume inside expands, and then when the motor is detached from the end of the robot, then the fold pattern is released and it reverts back to its extended state. And you can use these sorts of ideas in, for example, swimming, where if you put this robot underwater, then it'll inject and then expel water that'll allow it to push itself forward, right? So in this case, again, the compliance of the robot is extremely important to its behavior. And so here, instead of just thinking about, well, what is the payload that a legged robot needs to achieve, and therefore what's the stiffness of the leg, we're trying to think about, well, what is the influence of the surrounding fluid on the robot? How does the interaction between the softness of the body and the surrounding fluid affect its forward locomotion and its cost of transport? And so zooming out then, our big idea is how do we, now that we have these algorithms that allow us to design for particular compliance in different scenarios, how do we figure out what are the task objectives, right? How do we actually map the particular behavior that we want the robot to achieve in terms of trajectory or energy efficiency or, something else into something that we can evaluate, so then we can use it as the inputs to the algorithms that I've shown. So to close off, I'll just note that all of this work was done by my lab members, both human and non-human, as well as in close collaboration with a lot of really amazing people. And with that, I'm happy to answer any other questions.
Okay, we have 2 minutes for questions, and I'm glad we got the chance to answer some already, but what do we have left? Yeah.
Would it in theory also be possible to include the choice of actuators into the optimization, or is it always a decision by the human?
Yeah, the question was, can we also incorporate the choice of actuators? Yes, and that's a slide that I skipped over, but let me pull it up real quick. That there is a question about what are the actuators that you actually want to use in this robot, right? Because the actuators need to produce the right forces and speeds and whatever else that you need to move the design. And so a lot of existing computational design systems will assume you're using a particular actuator. It's just whatever they have in the bin. But what we've been trying to figure out is, now if you have a particular dynamical response that you want from your robot, that gives you certain actuation requirements, right? And those actuation requirements can be used to pull from a database of motors which one is the most appropriate. But at the same time, that motor and the associated electronics, control, transmission, et cetera, will add mass to your robot, which then affects its dynamical response, right? So what you end up with is some sort of iterative design loop where you have to try to figure out, well, given a particular robot, what's the correct actuation? Given a particular actuation, how do I want to change the robot design? And this is one place where we've started to try to think about interdependency between modules of robot design, not trying to design them both together simultaneously, but more iteratively going back and forth.